So thing number one to go over, on Tuesday of next week, we are casting. And so I will send you an email on Monday that says where to meet. It's in the art annex, which is the building that is off separated from the art building directly in front of Carver. And you meet on the side of the building that is opposite Carver. So on the back side of that building, if you go in the double doors, they're down a little bit of a hallway, you go in the double doors and that will let you into the classroom. The foundry might be open when we get there. I'm not sure if those doors will be open, but we'll meet in the classroom. We'll go out and see him start the foundry and begin to melt the material. And then we'll go into the classroom and we will discuss extrusion and drawing in the classroom. And then we'll watch the pour. We will need approximately 3 people who would like to help with the pour. To do that, you have to wear shoes that won't start on fire. So unplastic shoes. They need to be leather if you can. Boots are the best, but something that will not start on fire. You should have jeans on because they are less likely, or cotton pants, they are less likely to start on fire. You'll be in an Elvis suit, but just for certain. And you would need to have your safety glasses there as well. So anyway, I will put that in the reminder as well to have some people help with that. He will tell you what to do, how he'll communicate with you, and what you'll do in lifting the metal and moving it around. Or there's also a person who has to guide, because the 2 people who are moving the metal can't see very well, and so they can't see side to side, and so it takes somebody else to guide them to each of the molds. So that is Tuesday. Thursday, we're not having class or lab, since not everybody, but lots of folks are going away. So that means we have to figure out something to do with Thursday's lab. I think the best thing to do would be if Thursday lab people came on Tuesday. The problem is it will really overload the 1 p.m. to 3 p.m. if all of the Thursday people come during that time. So it would really help if some of the Thursday lab people would be willing to come in the 3 to 5 p.m. lab so that we can just spread out a little bit. We're working on the lathe that day, and so we're already a little bit constrained space-wise. So 24 people gathered around the lathe would be a bit much. But anyway, I will leave it to you to decide which lab works for you, but come on Tuesday to lab, and we'll be talking about sort of the basics of how the CNC machine works, and we'll be running the parts that they go in the bearing, so it's the little thumb holder for the bearing for the fidget spinners. Remember that after next week, your fidget spinner designs are due on Monday morning, so not this coming Monday, but the following Monday. However, if you're going to be gone at the end of the week, you might want to work early on that, because, you know, CAD is fun, and you get to do CAD. Is that all sound okay?
Phenomenal.
Yes.
So we're casting during like the normal class period?
Casting during the normal class period, yeah. They will only let us cast 1 time, and so instead of figuring out how to do it all during 1 lab, we do it during the class time.
Can we make a sign-up sheet on Canvas so we know who all is going to which lab, so we know how to organize ourselves?
I can do that, yes. Item number 2. Item number 2 is that we have a sign-up sheet for Dine and Dash on Monday and Tuesday nights. So 6 to 7:30. It is, so we live 1 mile from campus down on South Hill. It is an easy walk down Garden Street to get there, or an easy bike ride, or an easy drive, or one year, one person, one wheel, maybe 2 people, one wheel there. It's easy for any of those. You can scooter. Frankly, I don't care how you get there. That's up to you. Anyway, so we'll have this, and maybe at the end of class we'll let people sign up for this. Can only take 12 at a time. It ends up overloading our house pretty well. Yes?
What is it?
What is Dine and Dash? Dine and Dash is an opportunity to come eat dinner at our house, and then the dash part is to go do whatever you have to do. So it's just
Dash
dinner.
part is to leave?
Yeah. Don't stay. Come to the house, go away. So anyway, it is just an opportunity to be together and to enjoy time together, but then also to not get in the way of other things that you have to do in the evening and such. I don't know exactly what we'll be having next week. Tonight is taco night, but anyway. It's Taco Thursday for the tooling class is what it is.
Taco Thursday tooling class.
And yeah, and then there will also be one next Wednesday night as well. So it's just this time of year. It used to be that my kids, like 1 year we did smoked chicken. By the end of 4 straight nights of smoked chicken, my kids are like, I'm so tired of smoked chicken.
You have children?
I do. They're both in college now. We will get to see them there.
Can you invite them?
They won't come. You know, teenagers. Actually,
Teenagers in college?
only one of them is a teenager. One of them is. Yes.
Do you like survey size?
No, not for this. No.
I think it'd be asked.
Yeah. Okay. Any questions before we move on? Because we need to move on to rolling. What?
It's not pertinent.
Okay. Rolling.
That is pertinent.
Keep them doggies rolling, right. Don't try to understand them, just roll them random and
Is this a real song or are you making this up?
All right.
Did you want us to sing?
No, you don't have to sing.
You will.
You have a slideshow.
We'll sing another time. You actually, you'll sing another time. All right, but we're going to read together and we're going to talk about rolling. So rolling is another bolt forging process. It is like forging, except that we're using rolls and it's a continuous process rather than slamming into the part over and over. So we have 2 rolls. They can be cylinders, they can be shaped so that they put a final shape into a part, and we squash the part down. All right. You don't need to memorize these or to write them down. This is just information so that if you hear these terms, you know, that is a piece of rolled material. So rolled material has lots of different names to it, and the names are sort of based on the broad shapes of the material for slabs, blooms, billets, plates, sheets, strips, foils, and then final shape. So all of these different size materials are rolled, and 90% of metal products were rolled at some point in their lifetime. So usually getting them to the right size stock at the very beginning is the most commonplace, but some things, whether it's sheet metal or foil, are rolled to their final size, and also things like railroad rails and just tubes and things are rolled to their final shape. Some structural shapes as well. Okay, we can roll things when they're hot, or we can roll things when they're cold. Much like we talked about with the other differences between hot work and cold work. If we roll it while it's hot, the material is more ductile, so we can deform it more, and that's kind of nice to be able to deform it more to a higher strain, and we can also allow it to regrow the crystalline structure so that we can then do more work on it afterwards. But we have the same problems we have with the other materials. If we hot work it, it will interact with the environment really quickly. It closes the pores and defects that are in the material because it's recrystallizing all the time, so that's nice. And the material will recrystallize after you roll it, so you don't get the texture, you don't get that shaping of the grain structure that, that you get with cold rolling. So that's kind of nice. The forces for metalworking when it's hot are a lot lower, but the pieces of equipment are a lot more expensive because they have to withstand the high temperatures. So, or the materials are more expensive. So it has good and bad. If we do cold rolling, just like with other cold forming, it gets us to the right shape, the final shape. It can have sharper edges. It is not going to have scale that grows on it, but we are limited in how much we can strain it. So we can strain it about 20% before we have to do something to increase the ductility again. So we can heat treat it or a number of processes like that to try to recover ductility. Whatever deformation we do to the grain will be permanent and it will stay in that way. And so cold rolled materials have a structure, the texture, where the grain structure is lined up with the direction of rolling that you did. So. It was a squeak.
Is
Yes.
roll pieces ever, is it foolish to ever like assume that it's like, or to think that like an extrusion can be rolls in a way and it's just being called the wrong thing? I feel like some extruded pieces I've seen could definitely have been rolled in a way.
So extrusion and rolling are two different processes, and they have different material structures and different needs. However, it is true that you can make a lot of the same materials by either rolling or extruding.
Okay.
And so it's just a decision based on the material properties that you want to have, the equipment that you have where you're working. Extrusion takes a lot less space, rolling takes a bunch of space. And so you just, but rolling is faster. So
yeah.
There are reasons to make the decisions between the two, and it is very true that you can make a lot of the same parts both ways. Not all parts, but many of the same parts. Okay. So if we roll something, where do we end up on the stress egg? This ends up being surprising. And it's surprising. So here I have the bottom roller. So I have some material that's coming over here. And it seems like I am just squashing from the top and from the bottom, so I ought to end up right at the sigma F point on the stress egg. But what actually happens is as I am squashing these two, the material both wants to get longer, but it would like to get wider as well. And the friction along the roll prevents it from getting wider. So it actually happens at this 1.15 times sigma F. And the fact that it can't get wider leads to some really interesting things that happen when you are rolling. So one of the things is, by the constancy of volume, if I have a certain volume of material coming in at a certain rate, the same volume of material has to go out the other side at the same rate. Okay, but if it's coming in thick and it's going out thin, but I have to get the same volume out, and the friction keeps it from getting wider, so it's getting thinner and it's getting longer, that means that when it exits, it has to be going faster, because I have to get rid of the same amount of material, but it's thinner. And so what happens in rolling is that the material comes in at one speed, it leaves at a different speed, and because it leaves at a different speed, if you think the roller is rolling at some velocity, The material's coming in at one velocity, it's leaving at a different velocity. Well, that means the material is accelerating through the rolling process. And what that means is that there is only one point along the roller where the roll and the material are going the same rate. Well, where you're on the thicker side, the roller is going faster, and when you're on the thin side, the material is going faster. So what this does to rolled materials is it burnishes a surface.
Say that
What is
again.
burnish?
Burnish, it polishes, it just rubs against it and it makes it smooth. All right, so here's one of the mysteries of life. One of the mysteries of life is, why does aluminum foil have a shiny side and a not shiny side? And it is, yes. That's why
So
we're
much of a
discussing
mystery.
that. Very good. So, you know, in marketing, they'll tell you, oh, well, this side reflects and this side doesn't, and all these other things, but that's not actually the reason. That's just them trying to justify the product that they've made. So we have this foil, and because of friction, we're down here at 1.15 times sigma f. It turns out that as the material gets thinner, the roll that you have to use to roll it has to get smaller in diameter. And with foil, you are down in such a small range that the diameter of the roll has to be really small. So they can't actually make that small a roll and have it apply pressure. So what they do is they take two pieces of foil and they put them together. The other thing that they're doing here is that the roll is so small that it's hard to apply 1.15 times sigma f down on the piece of material. So if we think about the egg, and we think about how could, if I have a material and I want to squash it, it can't get wider, it is getting longer, how could I use the egg to reduce the squashing force that I'm having to put into it? You could pull it, right. So I could grab it, and if I pull it, then I'm bringing it back along the stress egg, maybe to sigma f, or maybe if I'm lucky, I can come over here to 0.707 times sigma f if I were pulling really hard. Well, you can't pull on one sheet of aluminum foil that hard, but if you double it, if you put it over on, you know, two sheets, then you can pull harder on it, and that will actually reduce. It helps you in several ways. It reduces the force that you're having to put on it, and it also allows you to use a bigger roll. Well, the one that's on the side that's on the outside against the roll gets burnished, so it's shiny. But the side that is against the other piece of aluminum foil is not getting burnished, and so it's the dark side of aluminum foil. So they'll tell you that it is, you know, a feature, but it's an excuse. That's what it is. All right, here we go. Yes, nice, good. All right. All right, so as this is rolling, we see it coming out of the furnace. It is, the bright white piece is the piece of metal. It is hard to look at because it is so bright. Now notice it's going to go through a 3-high roller a couple of times, and then they're going to stop doing that. So we want to know why they stopped rolling it through the 3-high roller. And we'll talk about why they use a 3-high roller in a minute. Notice on this, over on the left side, there's a giant flywheel to keep the rolls spinning at a good speed, even because when you put the material through them, it tries to slow them down. So the big flywheel helps keep them going. Burning stick of metal. It is hot. Glowing hot. It's Look how long that piece of metal is now. It is still going by. In a minute, oh, there's the end.
It's so much longer.
Yes. But as we go down here, look at the speed of the rollers. So you can see the speed of the rollers as it goes. This thing chops it into shorter pieces. And the further down you go, the faster the rollers are going. A little hard to tell now. Open bearings are easier to see. There's a lot of water there. That's to cool the rollers. This is a device that cuts the material to make it into shorter pieces. You've seen enough of this line for right now. So at the end, it's looking. Right? It is really going fast when we get to the end. So there used to be one of these that unfortunately got taken down. It was this plant in India, and these rolling mills are often a half mile to a mile long. They just keep going. And at the end of this one, it turned the corner and went back. But they had this huge floor area because they needed to slow it down going back. When you start down the set of mills, it's going really slowly. By the end, it can easily be going about 60 miles an hour. And so you need to slow it down to feed it back into the other direction. You don't want to have to start that at 60 miles an hour and end up at 100 or something. And so they had this giant area that was sort of take up extra material as it comes hurtling out of these machines. And then when the end comes out, it comes out like a whip. And you know, it just looks like a bright stick. It's hard to imagine what this is, but this is like an inch diameter piece of steel. And so if you got hit by it, it would be awful. And so in this plant, there are all these people walking around working. It was India, so it's super hot. They're all wearing flip-flops and shorts, walking around working. And the end of this thing comes flying out and flying across the floor, and the guy just goes like that and jumps over and he goes winging under. So, yeah, that video got taken down, curiously. Anyway, so we see that the speed increases as it goes, and the speed is increasing because we're reducing the thickness, so it's getting longer. So by constancy of volume, it has to go faster. All right, let's talk about what we do here. So one way to roll things is to run them through a set of rollers and then run it back through the same set of rollers. You move them a little closer together, then you move them a little closer together, and you roll it back through. That works when you're doing the powering, but on an industrial process, that doesn't work very well because these giant rollers, you have to take them, you have to slow them down and stop them and then reverse the direction so that they can go the other way. And that's a huge amount of wasted energy. So instead, what they do a lot of times is they do a 3-high reversing. So now you can put the material through the bottom, and then you lift it up, you run it back through the top, and those rollers can just keep turning the same direction all the time. Why did they stop that? In the video, they did that several times, but then they stopped. Why not just keep doing that? It seems a lot easier than having a mill that's super long in all those stations. Yeah.
Because you have to stop the material.
You do have to stop the material.
On a straight line, it's going to be accelerating so fast, you don't want to stop all that material and reverse it.
Okay, it is a ton of, yeah, and
Yeah.
it's a ton of momentum. It's super heavy, so that's some of it.
Also, like, the bed would have to be like gigantic because it just kept going back and forth and back and forth. That would be a giant like bed bed on hydraulics going back and forth.
Yeah, it's getting longer and longer, and at the end, the piece of material was sort of that half-mile long. So then you'd have to have a mile to have a half-mile on each side of the bed. Becomes pretty untenable. All right. Also, as the material gets thinner and thinner, you have to reduce the diameter of the rolls that are rolling it. And so you need different rolls at the beginning than you need at the end. Turns out that making the roll strong enough is really challenging. We're going to go past that for a minute. Because you get deflection of those rollers. If we have a big roller across there, you can see how it could deform the part. But if you get to a small roller, the roller's going to deflect rather than the part. So what do we do about that? Well, there are several things we can do. One is to make the roller the wrong shape so that when it deflects while it's rolling, it becomes the right shape. That seems kind of cool, but it doesn't work if you're doing it over a really wide part. This only works for something that's fairly small. So instead what we do is we back up the roller with another roller. So if we have a little roller, we put a big roller behind it. Well, you can see that this 4-high roller, that's not going to be able to do a very wide part because the little rollers would just squirt out from underneath the big rollers. So we're going to have to do something better than that if whatever we're pressing is getting very wide. And so you can do a 6-high mill where now we have a big roller backing up a little roller, backing up a little roller. Or if that wasn't enough of a cluster, we can do a cluster mill.
No way!
So this is what actually happens. So just to have 2 rollers, we have to have all these other rolls to back it up because the little roll has to be backed up by slightly bigger rolls, which have to be backed up by even bigger rolls. And so there is the bearing set that is just looking at it from the edge. You can see that is a lot of rollers just to support those 2. So when you get to doing something like foil, every rolling stand looks like this. All right? Every rolling stand. Crazy. All right. Let's go back and look at or how they do train rails. And we will see, you know, those other jobs that somebody asked about, how would you stand doing that job all day long? We will see a worse job, especially if you don't like the person across from you. So watch for that.
In the early days of the railroad, train rails were made of either cast iron or wrought iron. Cast iron was too brittle and would break easily. Wrought iron was too soft and would wear out too quickly. So steel eventually became and remained the train rail metal of choice. The train wheel's rim runs on the inside of the rail to keep the train on the track. This plant makes train rails entirely out of recycled steel from scrap yards, food cans, and recycled pieces from the rail-making process itself. Electromagnets pick up the scrap and dump it in a charging bucket. A truck hauls the bucket inside, where a crane drops the contents into a furnace. An intense electric current melts the scrap steel at 1650 degrees Celsius. It then flows into a large brick-lined ladle, where they add carbon, manganese, and other elements to make the steel more durable. The alloy then runs down a ceramic tube that shields it from exposure to oxygen, which would ruin the metal. From there, the molten metal flows into molds which extrude it into continuous rectangular blocks called blooms. Acetylene torches cut each bloom into 3.5-meter lengths. A crane then transfers the blooms to a furnace, which, over the next 5 to 7 hours, reheats them to 1250 degrees Celsius. This softens the steel for further shaping. Then the reheated blooms enter a machine called a rolling mill, which elongates each bloom more than quadrupling its length. A shear then slices the longer, thinner blooms into 4 pieces. The pieces now go into another furnace for reheating. This preps them for the next set of rolling mills, which will gradually form them to the final rail shape. Different railroads used to use different shaped rails, which required changing the train's wheels when passing from one railway to another. By the turn of the 20th century, the T-shaped rail became the industry standard and remains so today. For the final shaping, each steel rail passes several times through 3 consecutive mills. This is what a mill's rollers look like. And here's the standard T-shape to which they form the steel. Next, a saw slices off about 30 centimeters to square off the ends. The cut-off pieces go back to the scrapyard. Meanwhile, the rails are laid out until they cool to about 500 degrees Celsius. Then an electromagnet piles them in a holding box, where they sit for 10 hours until they cool to about 90 degrees Celsius. When they come out of the box, they run through 2 sets of rollers. The first set flexes the rail vertically. The second, horizontally. This flexing process straightens out the rails, which curve slightly due to all that heating, shaping, and cooling. Next, each rail passes over a mirror, enabling inspectors to examine the bottom as well as the top. Finally, a saw cuts the rails to whatever size the railway ordered. Most often, the standard length of 25 meters. The quality control department measures random samples to make sure all the dimensions are precise. Every rail bears a number identifying the batch of steel from which it came. In the event of a problem, that number lets them trace all the rails made from the same batch. It's a system that ensures a safe, smooth ride.
So a lot of rails now are a half-mile long. So they no longer make they do make them in the 40-foot long versions, and some places that's what's used, but on a lot of the bigger railroads, they make them in half-mile long versions. How do you get a half-mile long rail to the place you need to use it?
A train?
Yeah, but how do you go around the corners?
You don't. Straight
Oh,
line.
straight up.
Oh, that's genius, Wes.
Yeah, well, the rails bend over a half mile. The rails bend because you're going to have to put them down and bend them to the shape that they need to be, and so they're just that flexible over a very long length that they just bend back and forth on the train as you take them where they need to go.
So if you're sitting on the end of it, you can just pull it
Well,
down.
if
Well, if
you're
you're
really
strong
buff.
enough.
Or if you have a lot of hydraulics. Yes. I would choose the hydraulics, but you know, you be you. Could I?
Could you
no,
could you
I
do it?
could not.
Make Bill carry it.
How long would a train track have to be before it goes over?
Dude, I'm carrying it.
The problem is they get heavier with their length, so.
What?
It's fine to have a
Yeah.
media.
All right, yes.
Are rollers also made out of steel?
Yeah, usually they would be made out of very high strength tool steel, and then occasionally you have to go to something higher strength, like tungsten or something, but then they're incredibly expensive.
I feel like they use so much steel to make more steel, like.
Yeah, where are we getting these
so
steels from?
silly. Like, how did they make the first?
Well,
What came first?
You're asking a real question.
Chicken or the egg? Okay.
well, you keep increasing the strength of what you're making. And then at the very end of the process, you rub it with rocks to make it the right shape.
Rub it with rocks?
Well, you grind it, which is like
Grind it with rocks.
rubbing it with little tiny rocks. So you grind it to make it the shape that you need.
There's gotta be an original. There's gotta be
Yeah, which
the
one was
original
first?
OG roller that made the rollers.
You don't have to have a roller to make the roller. The question is not the question is not the roller to make the rollers. The question is the lead screw to make the lead screws. Because at some point you had to make the very first lead screw, which moved the axes back and forth to make the first machine that made all the rest of the lead screws. And it was carved by hand out of wood. Yeah. Well, the very first one was made out of wood because you have to get the right shape even if you're going to cast it. So the very first was hand carved out of wood to cast and make the right. Okay, if you're in lab this afternoon, we are outside in whatever rain, except we're under the canopy. Maybe not your best jacket, but anyway, whatever.
Oh, I know. He's already has fiberglass.
And then on Tuesday, we are meeting at the Art Annex, that's right. If you would like to sign up for Dine and Dash, it is
Wait.
right there. To sign up for Dine and Dash.
Why does everyone want to go on the day that I go?
I guess it's popular.
Probably Monday.
Okay,
What do we got?
but all four of us.
Monday.
Monday's
Can't have
fine.
eggplant.
Okay. I'm gonna go nebulize and mix.
I think so. My mom is